All of you note this discussion carefully. There are two persons. There are two persons standing on the floor. Right. This person is a fifth standard person. Fifth standard. He is studying in the fifth standard. Right. Small boy. Right. Let us say his name is Mahendra Singh. Mahendra Singh. Okay. Right. Here I am standing. I am standing here. My name is Solai Murugan. Right. Yes, Solai Murugan. My name is okay, yes, sir. Right. My age is 45. Okay, right. So I'm the bigger person comparing to the small boy. Right. First, it means my capacity is very big. My capacity is very big. The boy capacity is small. Right. Just to keep this in mind. Right. Now I'm going to apply. I'm going to apply load on Mahendra Singh, the small boy. Okay, right. So how much load I am going to apply? I am going to apply 1 Newton in 1 mm square area. 1 Newton in 1 mm square area, right? So 1 mm square means very small one, right? In that 1 mm square area, I am going to apply 1 Newton, right? So the applied load is 1 Newton per mm square. Okay, right. So when I apply the load, the boy will try to be in equilibrium. Not only that boy, every object in the world is trying to be in equilibrium. Okay, right. So when we are trying to disturb it, they want to be in equilibrium, right? Up to some extent. Okay, right. Now, how much resistance this ms will be offered, right? Sir, same amount of resistance, sir. Same amount of resistance. 1 Newton per mm square. Why? If we offer less than 1, for example, 0.9 Newton per mm square, what will happen? He will fall this side. He will fall right side. Okay. So, not right this side. Huh? Right. Suppose he is offering more internal resistance, 2 Newton per mm square. Right. He will fall this side. Right. But ms want to be in equilibrium. That is why he is offering exactly same as that of external load, right? So the internal resistance it is developed by the boy. Internal resistance. Okay, right. It is applied, it is developed. Okay. Now we are going to increase the load level. 10 Newton per mm square. 10 Newton per mm square. Right. 10 Newton per mm square. What will be the resistance developed? Tell me. Answer, please. What will be the internal resistance developed by the boy? 10. Very good. 10 Newton per mm square. Right. Now we are going to concentrate on unit. Right. What is another name for Newton per mm square? Commercial unit. Newton per mm square. Megapascal. Okay. Newton per meter square is Pascal. Newton per mm square is megapascal. Okay, right. So hereafter we will introduce that megapascal. Okay, right. Now we are going to increase the load. Right. 100. or 150. Let us say 150 megapascal. Right? The resistance will be again 150. Right? Again, I'm going to increase the load. 300 megapascal. Right? The resistance will be 300. Okay. Right. Again, I'm increasing the load. I am increasing the load, applied load, 349 megapascal. Right? The resistance is 349 megapascal. Okay, right. So I will stop here. Okay, test is temporarily stopped. Right. So up to 349, externally applied load per unit area is equal to internal resistance offered by the body across unit cross section area. Okay, right. So what is the name for this parameter? Internal resistance offered by the body across unit cross section area. What is the name we can give? Stress. Very good, very good, very good, super. Stress. Okay, right. Internal resistance offered by the body across unit cross section area is stress. It is also stress. It is also stress. It is also stress. Right. Now tell me, answer my questions. Stress will vary or not? Stress will vary or not? Yes, it will vary. Stress will vary. Okay, right. It will start from 0. When the external load is 0, stress also 0. Okay, it will vary. Right. That is one thing. Right. Stress depends on which parameter or when the stresses are changing. Right. When the load is changed, stress will change. Or when the area, right? When the area is changed, stress will change. Okay, right. So stress depends on externally applied load and the cross section area, resisting cross section area. Okay, right. So stress depends on external load and the resisting cross section area. Okay, so that you will highlight. Stress depends on P external and resisting cross section area. Sir, what is resisting cross section area? Critical area. For example, there will be the object larger diameter. This is a smaller diameter. We are applying the load here. Okay, right. This is 2 meter square cross section area. It is 1 meter square cross section area. What is a critical area? 1 meter square or 2 meter square? Which area will be suffered a lot? Which area will be suffered a lot? 1 meter square or 2 meter square? Load is common for both. 1 meter square. 1 meter square area will be suffered a lot. Okay, that is a critical area. That is a critical area. Actual resisting cross section area. Okay, right. Right. So stress depends on external load and resisting cross section area. Right. So stress is a geometric function. Very important point. Stress is a geometric function. It will vary. It will vary. Okay, right. It depends on external force or external load and the resisting cross section area. Okay, right. Very good. Now, see, I'm a elder person, 45 years old. He is a very small boy. Okay, 10 years old. So my capacity is big, bigger one. His capacity is, the boy's capacity is very smaller one. So he cannot withstand my load continuously for a long time, because continuously I'm increasing the load, right? But the boy cannot offer resistance continuously till end. Okay, right. Now what is happening? When I reach the load 350 megapascal, what will be the stress? What will be the stress? Tell me. Stress value, resisting value. Same 350, sir. 350. 350 megapascal. Right. It is stress. But unfortunately, what is happening? When I apply the load exactly 350 megapascal, the boy is failing. Failing. It means he is falling down in this side. Failing. Okay. Right. So it is a important point. This 350 is a important point, important value. Why it is important? In this value, in this stress level, the boy is failing. Okay, right. Now, so far I have applied the load, right? Now I am asking one of our student, right? I am asking one of our student, for example, what is name? Korean, right? Korean. I am asking Korean. Instead of me, he is joining, right? He is also our student. He is 25 years old. Let us say he is 25 years old, right? His capacity is also very big comparing to small boy, right? Now, when Korean is applying load continuously like me, 1 megapascal, 10 megapascal, 150, 300, 349, 350, like that, right? Now tell me at what load the boy, same boy, Mahendra Singh, he will fail. At what load he will fail? What is your expectation? Tell me. 350, same 350. Same 350. Very good. Excellent. Excellent. Same 350. The reason is 350 is his capacity, the boy's capacity. Whether I am applying the load or another person is applying load, whoever is applying the external load, right? The failure limit depends upon this boy, right? Now, instead of Mahendra Singh, right? Let us assume that it is mild steel, mild steel, mild steel, right? So the failure value depends upon the externally applied load or material. Tell me. Failure value depends upon material. Material means MS, right? Material. Okay, material property, right? Now, it is the maximum load carrying capacity, right? Shall we give another name? Another name. 350 is his, that particular parameter. What is the parameter? What is the name? Maximum load carrying capacity, like that. I can carry up to 700 megapascal. Korean can carry up to 500 megapascal. This MS can carry up to 350 megapascal. So these values are our which property? I can take the load up to 600 megapascal. So 600 is my which property? Give me some suggestion. Quick. Okay. That is ultimate one. Another one. Think. Maximum load carrying capacity. So our student is saying ultimate capacity. Another name. 600 is my maximum capacity. What is another name we can give? Rename. 600 is my strength. Very good, very good. My strength. 600 is my strength. 500 is Korean strength. 350 is MS strength, like that. Okay. So strength is a material property. Strength is a material property. Right? It will vary or not. Tell me. For a particular material, you are taking mild steel. Now, today we are discussing about mild steel. For the mild steel, strength will be varying or a fixed one. For a particular material, you are having the material in your hand. For the taken material, it is a fixed value. It is a fixed value, right? That is what we discussed, right? So whether I am applying the load, whether Korean is applying the load, the failure value is 350 only, right? So strength is a fixed value. Strength is a fixed value. Okay. So strength is a material property. Strength is a fixed value for a particular material. Right? Next information, right? This 350, right? This 350. We are giving another name for 350 as a strength, right? So what is happening at 350? Failure happening, sir. Failure happening, right? So at failure, or when the failure happening, at failure, the 350 is also stress. Already you told, right? Stress is renamed into strength. Stress is renamed into strength. Okay, right. So what is the definition for strength? Sir, stress at failure, sir. When the failure occurs, the stress value is called as strength, sir. Shall we say like that? Stress at failure.
The maximum stress a material can take.
Yes, correct. That is correct. Actually, that is a correct answer. So my expectation is simple answer. Stress at failure. Stress at failure. Shall we say? Stress at failure is equal to strength. Shall I say like that? Is it correct? When the failure occurs, yes, we can say, right? Strength is nothing but stress at failure. Strength is nothing but stress at failure. So definition. What is strength? Stress at failure, sir. Right? If they are asking further explanation, you can say, sir, maximum possible stress the material can offer, sir. Right? Okay. So stress at failure is strength. Strength is a material property. Strength is a fixed number. Strength is a fixed number. Three things, right? Similarly, previously also in the stress also three informations we have studied. What are the three informations for stress? What is the definition for stress? Internal resistance offered by the body across unit cross section area. Definition. Okay, right. Stress is a geometric property. Stress is a geometric property. It will vary or not? Yes, sir, it will vary. Okay, right. Now, when the failure will occur? Tell me. When the failure will occur in the experiment? Experiment is going on. It means we are increasing the load per unit area. Okay, right. When the failure will occur?
When more stress than what the material can take is applied.
You are correct. You say simple way. What is a simple answer? When this particular parameter is equal to another parameter, the component will fail, sir. Like that.
When stress becomes strength.
Very good. So stress value depends on you. Okay, because you are going to apply the load. Okay, so stress is in your hand. Stress value is in your hand. Okay, if you increase the load, more stress will be there. If you decrease the load, less stress will be there, right? So we can vary the stress by changing the load, right? When the stress is increasing continuously, when the stress is equal to strength, component will fail. When the stress is equal to strength, component will fail. Okay, right? That will highlight. Failure occurs when the stress is equal to strength. Okay, right. So generally stress is represented by sigma, comma, tau. Okay. So in the UG level, normal stress is represented by sigma. Shear stress is represented by tau. Right. In the advanced level, for example, if suppose if you are joining in IIT, right? In the higher studies, we will use only sigma, right? Based on the suffix, we will decide whether it is normal or shear. For example, sigma xx is normal stress. Sigma xy, different suffixes, means shear stress. Right? So symbol is not a matter, suffix is a matter. Okay, right. So the symbols used to represent the stress are sigma and tau. Okay, right now. The symbols used to represent the strength is S. Yes. Okay, right. S means strength. Sigma means stress. Okay, right. So when the component will fail, when the stress is equal to strength, component will fail, sir. Okay, right. So now we are going to write the notes in the detailed way, right? Stress and strength comparison. Stress and strength comparison. Right. Right. First point. What is the definition for stress? Internal resistance don't say P by A, right? Internal resistance offered by the body across unit cross section area. Right? See, never reduce the definition. Right? In all the interviews, people are expecting this definition only. Right? Don't say anything right, other than this. Right? Internal resistance offered by the body across unit cross section area is nothing but stress. Sir, what is a strength, sir? What is a strength? You tell me, what is a strength? What is a strength? Answer, please. Definition, sharp definition. Already we told. Stress at failure, that's all. Very simple answer. Stress at failure, sir. Stress at failure. Right. Next, stress is which property? Stress is which property? Geometric property. Stress is geometric property. Stress is geometric property. Strength is which property? Answer please. Strength is which property? Strength is which property? Material property. Super. Material property. Strength is material property. Okay, right. So already we discussed stress will vary. Stress varies. Stress varies, right? How it will vary? From which limit to which limit? See, when we are doing the experiment, at the experiment, stress will vary from 0 to maximum. Up to which limit stress will vary? When we are doing the experiment, up to which value stress will grow? Up to strength value. Very good. Up to strength value. 0 to strength. 0 to strength. Right. Now, let us assume that we are working in the industry. Okay. We are working in the industry. Our manager is asking us to design the shaft or rod. Rod. Uniaxial tensile rod. Uniaxial tensile rod. Okay. Right. He is saying that the rod has to withstand P is equal to 100 Newton. Material is mild steel. Material is mild steel. Okay. So please unmute. Anyone please inform him. Anupa. Right. So manager is asking us to design the rod, axial rod. Okay. Right. In such a way that it has to withstand compulsorily 100 Newton. The material given is mild steel. Okay. So what we will do? Initially, we will assume particular area, right? For example, particular area, A1. Okay. Right. Assumed area. Let us say that A1 is 10 mm square. Right. Load is let us say it is another number you will give. 1000 will give 1000 Newton it has to withstand. We have to design the rod. Right. Initially we assumed that 10 mm square. Right. What will be the stress? It is axial, simple tensile stress. What is the stress? 1000 by 10. How much? 100 megapascal, sir. 100 megapascal. 100 megapascal. Right. Now tell me how to take decision whether the assumed cross section area is okay or not. How to take decision? See, you have calculated the stress. Right? Just in the paperwork only, not in the experiment, right? In the paperwork notebook, you have calculated the stress for the given load and the assumed area. Right? Calculated stress is 100 megapascal. Right? Now, how to take decision whether the assumed area is acceptable or not, or the component will be safe or not. The component will be safe or not. Tell me. How to check? When the component will fail, when the component will be safe. Based on that, you can decide. Yeah, quick answer. When the component will fail, first tell me. When the component will fail, tell me. Quick answer. When the component will fail. Anyone, you can unmute and tell me answer. When the component will fail. When the stress. Very good, very good. You will verify whether the stress is equal to strength or less than the strength. Okay, right. Particularly whether it is less than the strength or not. Stress is less than the strength or not. Right. When the stress is less than strength, okay, component is safe. When the stress is equal to strength, component will fail. When the stress is greater than strength, component will fail. Sir, how the stress will be more than strength, sir? Right. See, it is not experiment. It is theoretical calculation. Say, right? You can assume 10 mm square, 5 mm square, 2 mm square, 1 mm square. Okay. For just assumption in the notebook, right? The component will not fail. No need to worry about it. Just we can predict whether it may fail or not if it is done in experimentally. Right? So in the paperwork, stress may be calculated, right? The value may be anything. The calculated value may be anything, right? Now, what will be the next step? Sir, I will check the stress with the strength, sir. I will check the stress with the strength, sir. Right? See, very important point. Very important point. Note this. Right? Now, we are going to check. Sigma is equal to 100 versus strength. Right? I am saying that strength is 80 megapascal. Strength is 80 megapascal. Now tell me, this 10 mm square, right? This 10 mm square is acceptable or not? Or your component, designed component will be safe or not? During this comparison, what is the decision taken by you? It is not safe, it is failure. It is failure. Failure. Okay, right. Failure. So how to make it as a safe design? Right? Whether I can apply the lesser load or I can increase the cross section area. There are two options. Okay, right. You cannot reduce the load. It is given by the manager. You cannot reduce the load. If you ask the manager, sir, shall I reduce the load, means what he will say? Why should you reduce? You need not apply the load. Let the component be free, like that. Okay. Right. So the load must be carried by the component. We should not reduce the load. You don't have rights to reduce the load. You don't have rights to change the material. Right. So only thing is, what you can change? You can change the cross section area. Okay, sir. I cannot change the load. I cannot change the material. I can change the cross section area only. So what I will do? I will go for next iteration. A2 is equal to 20 mm square. Right. What is the stress now? 1000 by 20 is equal to 50 megapascal. 50 megapascal, 50. Okay, right. Now tell me, the component is safe or not? Safe. Okay. Now it is safe. Right. Here, two things we have to notice. Right. During the paperworks, calculated stress value may be any number. Right. 1 megapascal, 2 megapascal, 100 megapascal, 10,000, 20,000, anything. Right. So theoretically, or hand calculations, stress can vary from 0 to infinity. At hand calculations, stress will vary from 0 to any number. Okay, right. Another information, right. How did you take the decision whether the designed component is safe or not? You have to explain. How did you take the decision whether the designed component is safe or failure? Anyone can answer, please. How did you take the decision? You took decision, right? Failure, safe, like that. You compared to number. Stress is compared with strength. That's all, right? Stress is compared with the strength. So during that comparison only, you took decision, right? When the stress is less than strength, safe, sir. Equal to strength, failure, sir. Greater than strength, failure, sir. Like that. Okay. So to take decision, stress should be compared with the strength. Very, 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 very important point. Ultimate point. Okay. Stress should be compared with the strength. Right. Now come to our notes. Right. Stress will vary at experiment. It can vary from 0 to strength only. When we are doing the experiment, when the stress is equal to strength, component will fail at any cost. Stress cannot be more than strength value, because when it is reaching the strength value, component will fail. Chapter over, right? But when we are doing the hand calculations, right, the calculated stress may be any number, 0 to infinity. Right? What about strength? It will vary or not? No, sir, it will not vary. Strength is a fixed number. Strength is a fixed number. Okay, right. Now, to take decision, you compare two values, right? Stress and strength. Who gave the value of stress? Tell me, who gave the value of stress? Who gave the value of stress? Did your manager give? Manager gave load and material only. Who gave the value of stress? Quick. We have calculated. Super. Right. We have calculated. We have to calculate the stress. We have to calculate. Right. Then how did you get this 80 megapascal strength value? Who gave that? Manager gave that, because material property. Once the manager told that the name of the material, for example, a manager told mild steel. Right. So immediately what we did, we went to data book. For the mild steel, what is the strength value? We have seen the strength value from the data book. Right. So strength value is available in the data book. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . available in data book. How the data book people will get this number, strength value? From the testing laboratory, from the internationally accepted or permitted testing laboratory, they will get the number. They will do the test in that famous testing laboratory. They will get that number from that lab. Okay, right. Next, what is a unit of stress? Tell me, what is a unit of stress? Internal resistance offered by the body across unit cross section area, megapascal, right? So stress, right? Unit is megapascal. Right. Now I'm saying one thing. Tell me whether it is correct or not. Strength is also a stress. Strength is also a stress. Right. Is it correct or not? Strength is also a stress. Yes, right? So the unit of strength is also megapascal. So students, don't forget, stress and strength must be communicated through megapascal. Young's modulus, bulk modulus, shear modulus, all the three modulus must be communicated through gigapascal. Right? Don't forget, stress and strength must be communicated by megapascal. Young's modulus, bulk modulus, shear modulus must be communicated by gigapascal. Okay, right. Next. What are the symbols we are using? For stress, sigma and tau. Okay. Sigma, comma, tau symbols. Okay. Sigma is generally used for normal stress. Tau is generally used for shear stress. Right. Already I told you, suffix is very, very important. Okay. Right. The two suffixes are same. XX or sigma YY or sigma ZZ. So these are all normal stress components. Normal stress components. Right. Suppose two different suffixes XY, YZ, ZX or XZ. So if we are having two different suffixes, they are called as shear stresses. Okay. So sigma XY can be represented by tau XY. Okay. Right. So strength is represented by S, symbol S. Right. Next point. Already you studied. How many stresses are available? Tell me. Answer please. How many types of stresses available? 7.
More.
Very good. Very good. 7. Right. Sigma T, sigma C, sigma B, bending normal stress, sigma thermal, 4 normal stresses, then tau turn, tau trans, tau torsion, 3 shear stresses. Okay, so totally 7 stresses are available. Right. How many strengths available? There are 2 types of strengths. There are 2 types of strengths. Tensile strength, and shear strength. Right? Tensile strength and shear strength. Right? Only 2 types of strengths. Right? Here I will write something extra, not now, after sometimes. Okay. Right. But name is tensile strength and shear strength. Two types of strengths available. Sir, to take decision, stress should be compared with the strength. That I know, sir. Right. Now I have doubt. Sir, which 7 type of stresses available? Only 2 type of strengths are available. Which stress should be compared with which strength? That is a question, or that is a doubt you have in your mind. Okay, right. So this is very, 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 very important information. See, which stress should be compared with which strength? Ultimate question. Okay, right. So for that answer is, first we have to decide. Which strength should be used for comparison. Okay, that we will discuss after 10 minutes. First point is, which strength should be used for comparison. First point. Right. Then, for example, we have decided to use tensile strength. Okay, for example. Now, let's say 7 stresses are available, sir. Which stress should be used? Right. You may think that, sir, normal stress, right? Normal strength. Tensile means normal, right? We can take any one of the normal stressor. No, it is wrong. Right? So you have to calculate equivalent normal stress. Sigma equivalent. Right? The equivalent stress will vary from minimum to maximum. Inside the material. You have to calculate the equivalent stress. Okay, right. These 7 stresses can be applied on the external surface of the component only. All the 7 stresses can be applied by you on the external surface of the component only. Right. After that, after applying the load, you have to go inside the material. You have to calculate the equivalent normal stress. Equivalent normal stress will vary from minimum to maximum value. Okay. Whether it is minimum equivalent normal stress, whether it is maximum equivalent normal stress, okay, both are called as principal stresses. Okay, right. So how can we say how can we define the principal stresses? Sir, the maximum possible internally developed, inside the material, very important point. The maximum possible internally developed normal stressor, that is major principal stress. Then what is minor principal stress? The minimum possible internally developed normal stress is called as minor principal stress. Okay, right. So don't forget. So sigma equivalent is nothing but principal stress. Okay, right. Now you may ask another doubt, sir. If I select sigma tensile strength, I have to calculate sigma equivalent inside the material. It means principal stress. The principal stress should be compared with the tensile strength, sir. Then I can take decision. When the principal stress is less than the tensile strength, safe, sir. When the principal stress is equal to tensile strength, component will fail, sir. When the principal stress is greater than the tensile strength, component will fail, sir. Okay, sir. That is clear, sir. I have another doubt. Suppose if I select the shear strength for the comparison, which stress should be compared, sir? Which stress should be used for comparison, sir? You may think that you can select any one of the 3. That is also wrong. From all the 7 stresses, you have to calculate tau max, tau equivalent, okay, tau max, right? So the tau max would be calculated from the externally applied 7 stresses. Where you have to calculate the tau max? Inside the material, right? This tau max, where you are calculating? Inside the material, you are calculating. So the internally calculated tau max should be compared with the shear strength. Okay, right. Is it clear so far? Is it clear so far? Is it okay?
Yes, sir.
Yes, clear, right. Now you are taking the decision by comparison process, right? You know which stress should be compared with which strength now, right? I did not tell when we have to take tensile strength, when we have to take shear strength. I did not tell so far, right? We will discuss after some time, right? But you know, the applied stresses, externally applied stresses should not be directly used for comparison. That should not be directly used for comparison. We have to calculate either sigma equivalent or tau max. Compulsorily, any one should be calculated. It is nothing but principal stress. It is nothing but maximum shear stress, right? So after calculating equivalent normal stress and equivalent shear stress, you are going for comparison with the corresponding strength, right? The stress versus strength comparison, right? Stress versus strength comparison to take the decision whether the compound is safe or not. That comparison process is nothing but theory of failure. The comparison process is nothing but theory of failure. Right. Sigma versus S strength. Okay. So this comparison is nothing but theory of failure. Right. Civil students, for the structural area, not a subject, full area. Structural area means engineering mechanics, mechanics of solids, strength of materials, structural 1, structural 2, RCC, for all the subjects. Heart of the structural engineering is theory of failure. Mechanical students, for the design stream, engineering graphics, engineering mechanics, strength of material, kinematics of machinery, dynamics of machineries, then design 1, design of machine elements, design of transmission systems, finite element analysis, for all the subjects. Right? It means all are coming under design stream. Heart of the design stream is theory of failure. Heart of the design stream is theory of failure. Heart of the structural stream is theory of failure. Right? Now think about the weightage of theory of failure. Right? I will give one flavor. Right? Two discussions we made. Right? Principal stress is compared with which strength? I gave two examples, right? Principal stress is compared with the tensile strength. Very good, right? Suppose if you are calculating principal stress, major principal stress versus tensile strength, this theory is called as Rankine theory. That's all. Rankine theory of failure is over. Rankine theory of failure or maximum principal stress theory or maximum normal stress theory. 3 names: Rankine theory, maximum principal stress theory, maximum normal stress theory. Very simple, right? Now you are clear about theories of failure. Sir, next discussion, in the next discussion, we calculated tau max versus, then it is compared with the shear strength, sir. Right? This theory is called as Tresca theory or gust theory. Gust theory or Tresca theory or maximum shear stress theory. Generally, in our class, our students are calling it as a tau max theory, sir. Tau max theory. All are same. Gust theory, Tresca theory, tau max theory, all are same. Okay, right. So we are giving advanced information only. We will discuss in detail later, right? Rankine theory is suitable for brittle materials. Rankine theory is suitable for brittle materials. Tresca theory is suitable for ductile materials. Keep this point in mind. Okay, Rankine theory is suitable for brittle material. Tresca theory is suitable for ductile material. See, these are the preliminary informations only, right? We will discuss the theory of failure in detail, not now. Just information, basic informations we are giving, right? Because while discussing the theory of failure, you should not get shocked, right? You should feel that it is already, I know the basic introduction about theories of failure, sir. Why we are discussing the theory of failure, sir? What are the data required for theory of failure, sir? Like that. What are the data required? 7 stresses. Where the 7 stresses are there? In the external surface of the material. Right. Where you have to calculate the principal stress and tau max. Tell me, answer please. Where you have to calculate the principal stress and tau max. Inside the material. Excellent, excellent. Inside the material. Don't forget. Okay, right. Now, another information. These are all on the external surface. Okay, right. Now, from this, you are going to calculate sigma principal, right? Comma tau max. Where inside the material. Okay, right. So this calculation, right? Calculation between externally applied 7 stresses to calculate internally developed principal stress and tau max, right? Depending upon the strength comparison, right? This process is called as stress transformation. Very, 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 very important subject. Stress transformation. Right? There are 2 types of methods for transformation process. Right? One is analytical method, another one is graphical method. The graphical method is called as Mohr Circle. Mohr Circle. Right? Now you can understand, right, where we are using the Mohr Circle. So Mohr Circle is used to calculate the principal stress inside the material or tau max inside the material. What is the raw data you required for the Mohr Circle? Sir, these 7 stresses, sir. From these 7 stresses, or with the help of these 7 stresses, I can use the Mohr Circle. I can calculate whether tau max or sigma p, sir. Is it clear now? Where we are using the Mohr Circle? Is it okay? Yes, right. So this slide is very, 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 very important slide. I have to give one more information. This point and this location. In these 2 locations, I have to give extra explanation. Not now. Right. So now you are clear about stress and strength. Right. See, our subject is strength of material. Our subject is strength of the material. See the name. Right. But we will study strength in the first chapter only. In that too, in the initial portion only. In 1 hour, in first 1 hour, we will complete full strength details. Okay. After that, we will study all the 7 stresses. Then we will study about the transformation with the help of Mohr Circle and analytical method. Why we are doing transformation? In order to calculate principal stress and tau max. Why we are calculating the principal stress and tau max? Sir, we have to compare the principal stress with the tensile strength, sir. We have to compare the tau max with the shear strength, sir. Why? That is the theory of failure, sir. Why we are using the theory of failure? To take decision whether the component will be safe or not. Okay, right. So most of the work will be on the stress side and theories of failure side. Right? From the strength side, we have to study very less amount of informations. Okay, so final outcome: 7 type of stresses, 2 type of strengths. Right? Clear. Right? Now another information. Right? See, it is a beam. Right? It is a beam. See, in this class and the next class, we are teaching like a story, right? But each and every point, whatever we are discussing, right? Each and every point is important for TRB as well as GATE examination, right? Mostly these things will not be available in the textbook. Okay, right. So keep this point in mind. Then only you can answer the GATE question or TRB questions easily, right? So TRB students, don't worry. On behalf of you, I have collected the questions, right? I will discuss in the proper time. Don't worry, right? Not only Kerala TRB, right? Other state TRB also I have collected, right? Don't worry about the question bank, right? Right. So let us take this beam, right? I am going to apply central point load. Simply supported beam with the central point load. Okay. Simply supported beam with the central point load. Right. It is a beam. I have calculated the bending normal stress. I have calculated the bending normal stress. Right. Now tell me, in the top surface, while bending, in the top surface, which type of stress will be developed? In the bottom surface, which type of stress will be developed? Tell me. Answer, please. Answer. Very good. Top surface compression, bottom surface tension. In the simply supported beam. Very good, very good. Correct answer. Correct answer. Suppose cantilever beam. Cantilever beam. Okay. Right. Cantilever is subjected to point load at the free end. Now tell me, what is the stress in the top? What is the stress in the bottom? Top surface tensile, bottom compression, right? So you are clear about it. Very good, very good, excellent. Now we are going to discuss one interview question. One interview question. Okay, right. Now, while calculating, we are able to observe that bending normal stress varies linearly. We will discuss in detail in the corresponding chapter. Right now, we are going to discuss about interview information. Right. It varies linearly from top surface to bottom surface. It is bending normal stress. Right. In the bottom surface, sigma B, bending normal stress is equal to sigma T. Already you answered. The value is 200 megapascal. 200 megapascal. Right. The top surface in this point, right? In this point, sigma B is equal to sigma C, compressive stress, that you answered already. The value is minus 200 megapascal. Right. Now the interview question comes inside. Right? Which is critical? Which is critical? Both are having same magnitude. 200 megapascal, 200 megapascal. Which is critical? Tension or compression? Answer, please. Tension or compression? Okay, very good. Compression, right? Tension, compression. Okay, right. I will explain, right? Don't worry. See, that is what I am expecting. right? Whether the answer is correct or not, right? Don't be the audience. Try to be a participant, right? See, here you are saying somebody is saying compression, somebody is saying tension. One student is saying both, right? It is not a matter. I will explain. I will give the correct answer, right? But you have to answer. See this slide. There is a plate. There is a plate. Right. We are making a small cut here. We are making a small cut here. Okay. Right. We are making a small cut. Right. Plate with the crack. It is assumed as a plate with the crack. Right. The crack is purposely made by us. Right. Now, what I am going to do? I am going to. Yeah. Please. Doubt, please. What is a doubt? If you have any doubt, you can ask. Immediately, you can unmute and ask. Right. I know most of you are trying for TRB, right? TRB. TRB means Teachers Recruitment Board. This board is conducting exams for assistant professors and lecturers for engineering colleges. Right. Okay. So plate with the crack. Right. Now I am going to apply a compressive load. Compressive load. Right. Compressive load. What will happen to the crack? Tell me. What will happen to the crack?
It will get smaller.
Very good. Crack will be closed. Right. Crack will be closed. Excellent answer. Crack will be closed. Right. Sigma compression. Crack closer. Technical name is crack closer. Right. For particular value, 200 megapascal. I applied for 200 megapascal. Right. Same magnitude, but I am applying tensile stress now. Tensile stress. What will happen to the crack?
It will widen.
Very good. So it will propagate. Right. Sigma tension. Crack will propagate. Technical name is crack will propagate. Crack will propagate or crack growth. Okay. Right. Now you can understand, right? Why I asked that question, right? Now tell me which is critical, tension or compression? If the crack propagate like this, the material will be split into two pieces, right? So tensile is critical, right? Even though micro level cracks are available in the material, compressive stress is not critical because they will try to close the crack. But even if you apply small amount of tensile stress, they are trying to extend the crack, widen the crack, right? Propagating the crack. Right? So tensile stress is critical. Interview question. It was asked for me also in General Electric. I worked in General Electric for 3 years. For me, they asked this question. Not only for me, frequently, and these questions are asked in the industries. Okay, right. The question was like this: sigma is equal to plus 10 minus 100 megapascal. It means stress is varying stress. Right? It is varying from minus 100 to plus 10. Right? Now tell me which is critical. Which is critical? Minus 100 or plus 10?
Minus 100.
Plus 10. Very good, very good. Okay, right. So now you are clear about the comparison between tension and compression. Right. Now we will discuss only one thing, then we will stop here. Right. See, while calculating the bending normal stress, we observe different values at different locations. Right. In this point, it is 150. In this point, it is 100. See, I am not worrying about compression side. I am worrying about tension side only. Right. Here it is 125. Here it is 75. Right. See, these are all the stress values. At every location, I can draw the stress pattern. Right. Okay. Right. So out of these values, right? So it depends upon the given location. You can calculate the bending moment diagram, right? What is the bending moment diagram for this loading? Simply supported beam with the central point load. This is the bending moment diagram. What is the maximum bending moment for this condition, given condition? WL by 4 is the maximum bending moment. M max. Okay. So with this M max, BM max, bending moment maximum value, I have calculated the bending normal stress. What is the formula? 6M by BH square. 6M by BH square is the maximum bending normal stress formula, right? For rectangular cross section beam, right? With this formula, I have calculated in this location 75 megapascal, here 125, here 200, 150, 100, right? Now the question is to take the decision, theory of failure decision. Which stress should be compared with the strength out of 5 values? Only one type of stress. All are bending normal stress only. All are bending normal stress only. Right. So we need not worry about the other categories, torsion, tau transfers, other things and all. Right. So we need not calculate the equivalent normal stress and all. Directly, since only one stress is available, right? Directly we can select any one number. That number should be compared with the strength. Okay, right. Now tell me, which stress should be compared with the strength?
Highest,
75 or what? Which one?
highest.
Higher value. Excellent, super. Right. For example, suppose strength is 175 megapascal strength. Right. Mistakenly, if I compare this 150 with the strength value, what will happen? According to the comparison, what will happen? Stress is 150, strength is 175. What will happen? According to you, safe, right? Safe. But the actual beam will be safe or fail. Actual beam will be safe or fail. Fail. Where it will fail?
200.
At 200, at 200. Here it will fail, right? So it is your mistake, right? While communicating the stress value to the manager, right? You have to communicate the maximum value only, compulsorily. Okay. So what is the final decision or final outcome from this discussion? For comparing with the strength, maximum stress should be used. Sigma max versus strength. Right? Means maximum stress value.
Sir, I have a doubt.
Yes, please.
Sir, you said the maximum this material can take is, for example, is 175, right?
Yes, strength
So,
maybe.
so what if instead of 200 there was also 190? Would we consider 190 or 200?
Which is 190 strength?
No, sir, not the strength.
Stress.
I mean,
Stress.
the stress value, the tensile
Stress.
stress value.
One second. I will give. In this point, it is 190.
Yes, sir.
Okay. Right. Again, from all these numbers, we have to select the maximum value only. Maximum value, right?
Okay, sir. Got it.
Maximum value. So maximum stress value should be compared with the strength. Okay, right. Now something you have in your mind. Okay, that is why you asked this doubt, right? The reason is, sir, here I have calculated 200, sir. Here I have calculated 190, sir. My doubt is, suppose here, if I calculate in this point, it may be 210, sir. It may be 210, but I did not calculate. I have calculated in this location, in this location. From the calculated value only, I can select the maximum. In between, if there is some extra maximum value, what to do, sir? That is a doubt. Okay, right. For that, I will give one clue. Right now, according to your observation, what is a sigma max? According to your observation, what is a sigma max? $200. Very good. 200. Right. Now I will give some idea. See, this is the BMD. This is the BMD. Right. So the maximum bending moment location. Right. Maximum bending moment location. First you have to draw the BMD. If you calculate the bending normal stress in the maximum BM value, right? Maximum BM value, right? Here you will get the original sigma B max. It may be 210 or 220 or 230. Okay, right. So the calculated values from the student side, right? Whether calculation in this location, calculation in this location, calculation in this location, calculation in this location, calculation here, calculation here. From this, I have selected the maximum, that is 200. That 200 is compared with the strength. That is okay. But sometimes in some in between points, the original sigma B may be maximum, right? So how to check it? We have to check with the M max location. M max location, maximum bending moment location. Okay, right. So if you know this information, at how many points you will calculate the stresses? Tell me, at how many points you will calculate the stresses? Only one location, sir. Directly I will go here, sir. I need not, very good, super. I need not calculate in this point, in this point, in this point. These are all waste. These numbers are waste. These will be smaller values only, right? If I calculate at the M max location, that will be the original sigma B max. Okay. So for that, first step is bending moment, drawing the bending moment diagram. Then only we have to calculate the bending normal stress. Is it clear? Is it clear? Right. Is it okay? Huh? Yes, right. So what is the conclusion made here? Conclusion, for comparing with strength, right? Even though you have many values, you have to compare the maximum stress value with the strength. Okay, right. So with this point, we'll stop here. Thank you so much.